Hello, everyone. So let's look at a couple of case studies in which we used PhysicsAI to optimize the interior permanent magnet synchronous machine geometry. Um, so here I'll not go with all the introduction Diana provided. So it's domain neutral, so we can apply it for motor design also. So for this case study, we chose a permanent magnet synchronous machine which has a peak torque of 429 Newton meters and its power level is 212 kilowatts at 4,275 RPM. And this motor is 54 slot, 6 pole machine, and it has three phases. It's a three-phase machine. For the first case study, the main goal is to minimize the harmonic distortion in back EMF, and the second one is to minimize the magnet size. So um, that means like we are focusing on two goals. So let's look at what data we had to extract and then how did the physics AI got trained and then how are the results are looking like after optimization. So before we move on, so the steps that we need to follow is first we need to have our PM machine configured within Flux because all the results that we need to use as data to train our physics AI comes from Flux, and these are actually exported as H3D files. H3D files contains the information of mesh and also the quantities on those mesh elements. So it's important for us to have H3D files to be exported. So Flux can do that for us. So we'll set up our uh, machine within Flux. Then we call it in hyperstudy, which we already know. We are using this process from so long time to optimize our motor using hyperstudy and also Flux. So it's the same procedure. And then within hyperstudy, once we have the connection with Flux with the motor, we try to run a DOE, like all the couple of experiments, which will run all the experiments and then it'll store us all the uh, results in the form of H3D files. So that is nothing but the mesh and simulation data set that we are going to use to train our physics AI model. So once we train our physics AI model, we have the AI model. So we do no longer need the flux model anymore. So we are going to use the AI model within hyperstudy again to run our optimization. So that's the workflow we follow when we have to use physics AI to optimize the motor geometry. Now moving on to the case study. So for the first one, we only considered the dimensions of the rotor. I mean, inside the rotor, as you see, like the end points of the arcs, which are denoted by A2, A3, and A4, and then the angular position of the center of the magnetic polar axis, and then the polar distance of the center of the magnetic polar axis, and also the dimensions of the magnet so that we can consider uh, the goal on minimizing the magnet size. You are not restricted to only using the parameters within the rotor. We just took it for the first case study, but you can use as many parameters as you want. So once you have the parameters, since our is to minimize harmonic distortion, and the other one is minimizing the magnet size. But for to minimize the harmonic distortion, we need to have two quantities. First one is we should have the RMS value of the back EMF that we are getting from each model. So that is one model. And then the maximum value of the harmonic. So these are the two quantities that are needed for us to focus on minimizing the harmonic distortion and at the same time maintaining the same magnetic flux so that we are maintaining the RMS value of back EMF that is needed. And on the other side, our third quantity is magnet size, which we will directly get it from the dimension parameter that we have. So that is already there. So we don't need an AI model for the magnet size. So all we need is two models, RMS and harmonics, maximum harmonic value. So once we have that, for this case study, we ran a DOE for 540 runs, and we got both the models. And for to running the DOE, it took around 2 hours 40 hours, as you see, like with the 30 core machine. And then we passed on the data to PhysicsAI and to train the AI model. So we have two AI models, one for the harmonic and the maximum value of harmonics, and then one for the RMS value of back EMF. So to train these models, it took 4 hours. But again, this is without any assistance of additional resource. But as you add more additional resource like more GPUs, it can go much faster. And then once we got both the models, we used it for optimization, the AI models, and we ran an optimization which took around 2 or 30 minutes for us to get the optimum model. Now let's look at the comparison of what we have from the optimization. So first thing, before optimization, when we did a fit for a normal fitting model, like the fit models that are already available within HyperStudy, you can see that RMS value of back EMF is very good. The more the R square value near to 1, the accurate is a prediction. The farther it is, the not much, the fit is not good as the actual values that we got from FEM. So you can see that maximum harmonic value is away from 1. So that means the fit of the meta model is not that good. Whereas when you compare it with the physics AI model that is trained, uh, the physics AI model for RMS value of back EMF is as good as the meta model. Whereas if you compare for the maximum value of harmonics, this is very good because it is much more near to 1 compared to what you have in the maximum harmonic value. So this is one advantage where you can have more accurate model with physics AI. But on the other side, we did list on the time that it took. Since in the meta model, it's only the numerical data that you're using to fit, it took less time for you to get the fit model compared to physics AI, where you'll be using H3D files to fit the model. It took more time to train the physics AI and a model and then do the optimization. So that's the comparison in here for time. Yes, physics AI with optimization took more time compared to using meta model. But if we look at now coming on to look at the comparison of the models that we got. So if we look directly looking at the prediction errors, so the meta model, even after optimization, it reduced the magnet size, which is one goal that we were able to achieve, but it did not reduce the harmonics much. This is completely due to the prediction error that we have in the maximum harmonic value. Whereas if you look at the back EMF that we got from the optimization using physics AI, it did reduce the magnet size, but not as much as what we have from meta model. And on the other hand, if we look at the maximum value of harmonic, it reduced a lot. Now the voltage, back EMF voltage is much more sinusoidal and our harmonic value is reduced. So this shows that the magnet configuration the magnet shape and that we got is much more better and a good shape than what we have from the meta model. So this is like this is the upper hand that which we can have from the accuracy of physics AI compared to the meta model. So that is for the case one, where we took magnet size and then the minimization of harmonics within the back EMF case study. So where we have advantage of accuracy in prediction of the quantities, compared to the meta model, though it took more time to train physics AI compared to the meta model. So now moving on to much more complex case where it's not only the EM, because these days, or for the electric motors, it's actually the multiphysics simulation is very, very important, because it's not only from the EM side, it has to be stable. It has to run in a stable way under all the conditions. So the challenge is to consider all different types of physics for the optimization. So we should get all the data out of it, and then for all the different conditions like EM, rotor stress, motor temperatures, and also the also noise and vibration as well. So this makes it more complex. And then getting all the data and then creating the machine learning models makes the simulations much more faster. And from the previous case study, we saw that physics AI models are much more accurate. So we can rely on the accuracy of physics AI models for different physics simulations also. So looking at that, so I have a simple video to show you what we did for the multiphysics simulation. So me just to fast forward, because we do have the I did upload this video. We'll share the link after. So just to show you what we did. So first we had set up the PM model within flux motor to get all the data out of flux motor. And flux motor is like very versatile, so we can get EM data, noise and vibration data, and also thermal data out of flux motor. So we got all three data out of flux motor, except one thing, which is the stress, rotor stress that we need to get. We were using SimLab for this multiphysics design. And once we have all this, so this is to show you like how we actually configured the flux motor model. So we have the machine model in here with all the parameters. And then as I mentioned, like we can get the EM data from flux motor and also the thermal as well, and also NVH as you see. So this data, once you have the model, you can directly call it into hyperstudy. That's what that comes up as the next step. So you can call them into hyperstudy directly with the export option, and then call the exported connectors into hyperstudy. Use them to create the DOE that is needed with all the quantities that you want to use to train your AI model. So now once you have the DOE data, you can bring it into for into physics AI to train the model. So here we are showing it for rotor stress, where we use SimLab to get the rotor stress data as separate simulation of the rotor. And once you have it, you can train the model. So the lower the loss, the more accurate the model is trained. So once you have the trained model, you can also verify with what physics AI is predicting and what is a true value. And once you like confirm that, okay, this is predicting well, you don't need to adjust your model hidden layers or number of epochs that it needs to do. You can call all the physics AI models of the quantities that you already created using physics AI. So you can see we have AI models for um, EM quantities, and then also NVH, stress, and also temperature. So this allows us to do multiphysics optimization. And once you have it, you can call within hyperstudy and set up and do your optimization, like the normal optimization that you do. And after doing all this, so this is the final one that we got as the optimum model with overalls with power, more power with minimized magnet size, and the sound power level is less than 70 dB, and the maximum stress is only 400 less than 400 megapascals, and the maximum temperature is limited to 180 degrees centigrade. So this is the optimum design that we got. So this is like a small comparison for you to see how the initial and the optimum geometry is. So to compare the time it took for us to between the model, FEA model, and then the AI model, so you can see that the whole time that the physics AI model to give the analysis is just 63 seconds, whereas when we have to run all the analysis of different physics using flux motor simlab, it took around 960 seconds, which you can see that it's the AI model is 15 times faster. So here we got the time advantage also when we have the multiphysics simulation included. So then to summarize, faster computation, as we saw, we have time advantage when we have multiple physics combined and we want to do a multiphysics optimization. And the other thing, yes, multiphysics optimization is possible. And then the second thing is accuracy. So you can fit the model nicely as we saw in the rotor stress fitting. So the it's more accurate, and we can get the optimum design that we can rely on, that it is good design with respect to all types of all the physics that we have considered. And these are the two case studies that I have on using physics AI for motor design. Thank you.